Cool. Well, welcome to the Math 1325 Exam 1 review. Let's go through some introductions. My name is Nico Lahu, and I'm a math leader at the Peer Tutoring Center. And could the other leader introduce himself as well?
Um, Hello, yeah, my name is Shreeman. I'm also a leader at peer tutoring.
Cool. All right, well, let's get started for this Math 1325 Exam 1 review. So in today's review, we're going to be looking at three things, right? We're going to be doing a quick algebra review, and then we'll be taking a look at functions and then derivatives. Although, if I remember correctly, your professor mentioned that because of the winter storm, you haven't actually gotten to derivatives, but you guys have covered limits and continuity. So that's what we'll be covering in that section. So first, for our algebra review. So for polynomials, in algebra, it's always important to keep in mind PEMDAS, right? So parentheses, exponents, multiplication or division, and then addition or subtraction, right? So what is this? Well, this is the order in which that we solve polynomials, or we solve these big expressions. This is the order in which we do each process. So here's an example, right? If you look at the first line, we have 2x times, in parentheses, 3x, x plus 3y squared times x cubed plus y squared. Well, so first we take a look at the parentheses, right? Is there anything that we can solve or simplify out in here? And no, there's really nothing, right? So then we'll move on to exponents. In exponents, we have this squared up here. So we're going to be multiplying x plus 3y times x plus 3y, right? That's the definition of squares. And then after that, we'll deal with, multiplication and division. So we'll multiply out these two factors, which, gives us x squared plus 3xy plus another 3xy plus 9y squared. After that, times the other factor of x cubed plus y squared. Now, within this, right, let's deal with parentheses one more time, because it looks like there is something we can simplify. We can simplify this 3xy and this 3xy, right? They're common factors, so we can combine them. So let's combine them to a 6xy. Now after this, right, let's look at parentheses, nothing to really simplify. Exponents, nothing to simplify. So now I'll move on again to multiplication and division. And let's bring in this 2x, right? I'm going to multiply that into our factor here. So we'll get a 2x cubed plus 12x squared y plus 18xy squared, right? And then again, there's nothing to simplify. So we're going to multiply with this last factor. So we get this whole expression down here, right? This 2x to the 6th, 2x cubed, etc., etc. This is a quick example, and that's what I want to factoring. Let me fix, there you go. So when we're factoring, there are a few things to keep in mind, right? So first, you got to keep in mind about the greatest common factor. So within your parentheses, if there is a greatest common factor, that could be a constant or that could be a variable, right? So it could be like a 3x or could just be like a 4. Then try to factor that out of all the terms, right? And have it multiplying by the whole factor itself. And for trinomials, right? So what do I mean by that? I mean expressions that have the form ax squared plus bx plus c, right? And a, b, and c are all just numbers. So if a equals 1, then look for two factors of c, right? Two factors that multiply to equal c and add up to b, right? And it's going to take a little trying to figure out a little like combination work, but your goal is to try to factor them out in something that has like an x minus, a factor, so like a factor of c, and then x minus the second factor of c, so that these two multiply to c and then add up to b, right? So now, general trinomials, well, if a is not equal to 1, then you're just going to have to find factors of both your first term and your last term. So factors of a and factors of c. And you guys got to try different combinations until they work, right? Until this whole trinomial works. And lastly, you have special factorizations. So things that are in this format, you have the difference of two squares. So if you have something that's, something squared minus something else squared, then you can write it in this format. Or if you have a perfect square, look like that. and then the difference of two cubes and the sum of two cubes. So for these, it's there's like a little saying that goes, right, for these difference and sum of two cubes, right? You always think of SOAP, right? So SOAP. So when you're looking at your like original operation, in your factored out form, you have same, opposite, and always positive, right? Okay, so let's move on to a couple examples. So in our first example, right, it doesn't exactly look like a difference of two squares, right? Because we don't have like an x squared minus like a y squared, right? We have something to the fourth. However, you can imagine this fourth as like a p squared and that whole thing squared, right? And then minus 3 squared. So if that's clear, right, then we can just rewrite this as how we have it down here, right? So this factor in here plus a 3, and then again this p squared minus a 3. Now for the sum of two cubes, right, so we have m cubed plus, well, 125 is just 5 cubed. So we have an x cubed and a y cubed. So we can go ahead and fill out that formula. And just remember SOAP, right? We have same, opposite, and always positive. Okay, now for rational expressions. Well, so there are a couple properties of rational expressions that we have to keep in mind when we're simplifying these things, right? So, we have this fundamental property, right, that you can multiply by kind of like a fancy version of 1, right? So if I had the fact like the rational expression, p over q, and let's say I want to multiply by a fancy version of 1, right? And if I have anything divided by itself, then that's equal to 1, right? This whole expression here, that's equal to 1. So, and then when we multiply, if you look down here in this property, when I multiply fractions, I just multiply the numerators across and the denominators across. And that's how we get this PS times QS. Now for addition and subtraction, you got to make sure that your denominators are the same, right? You have common denominators. And after that, you just deal with the operation in the numerator. As multiplication, as I mentioned before, you want to just multiply straight across. So multiply your numerators and multiply your denominators. And lastly, for division, division is, kind of like multiplication, but with a little trick. When you're dividing by this fraction, r over s, you're actually multiplying by its reciprocal. And what do I mean by its reciprocal? Well, its reciprocal is technically 1 over your fraction, right? Although it looks kind of weird, it just means you kind of flip it over. So when you're dividing by a fraction, you're really just multiplying by, the flipped over version. So the goal of rational expressions is to use these properties to reduce and combine them, right? So let's look at this one example. And it is a big example, but that was my goal, right? If we can solve these difficult problems, then you guys will be just prepared for the test, right? So we're looking at x plus 1 divided by x squared minus 5x, plus 5x plus 6, minus 5x minus 1, x squared minus x minus 12. So let's bring in a little of our knowledge that we know from those trinomials, and let's try to factor these out, right? They all have an a equal to 1, so we're going to look for factors of 6 that add up to 5. So here we have 2 and 3, and if you see that works, right? So 2 times 3 is 6, 2 plus 3 is 5. So that's good factorization. And we'll rinse and repeat that process with this x squared minus x minus 12, and we get x plus 3 and x minus 4. So with this, right, we don't exactly have common denominators yet. So let's try to get that. If we can see, we both have an x plus 3 in both of our fractions here. But on this side, we're missing an x minus 4. And then on this side, we're missing an x plus 2. So let's multiply by that fancy version of 1, right? So that we now have common denominators, right? In our denominator, we have is x plus 2, x plus 3, and x minus 4. And the same thing over here. So we're going to multiply and distribute that out up here in the numerators, and I will subtract both our numerators. After that, let's drop the parentheses. Make sure you distribute this negative into our expression here, and then combine like terms, and we're ended up with this. Now lastly, you got to remember greatest common factor, and over here your greatest common factor is a -2. So we're going to factor that out and be left with a 2x squared plus 6x plus 1. Cool, cool. Now let's move on. Linear equations, right? So when working with linear equations, there is two things we have to keep in mind, right? We need to keep in mind the properties of equality. And what do I mean by that? Well, we have this addition or this additive property of equality, where if you have A is equal to B, you can add the same number C to both sides and your equation is just fine, right? This equal sign still holds. And now for this last one, it's kind of the same thing, but with multiplication, right? If A equals B, and then you multiply by a common factor C, then your equation still holds. And for quadratic equations, right, when we're solving those, we want to focus on using the zero factor property, right? Or factoring with the quadratic equation. So the zero factor property, well, what that says is if you have A times B is equal to 0, then either A equals 0 or B equals 0 or both, right? And for the quadratic formula, it's this big formula that, I mean, you've probably seen in high school or in other algebra courses. It's that negative b plus or minus square root of b squared minus 4ac all over 2a. And then lastly, for this one section, we have rational equations. So for rational equations, what you have to do is you have to multiply both sides of the equation by a common denominator to get rid of that fractional part, and then just solve the remaining linear or quadratic equation. Now, it might seem simple, but there is one extra thing we have to keep in mind. We always have to keep in mind if we get an answer that makes our denominator equal to 0, right? And that is not an answer. It's called an extraneous solution. You might know it as like an asymptote, or you might know it as a whole, right? And we'll see examples of that. Okay, so here is one example, right? So we have this 2 over k minus 3k divided by k plus 2 equals k over k squared plus 2k. Now, I chose a specific example because it works through rational equations and linear and quadratic equations. Right? So it really kind of works through both of those. So first, we're going to multiply by a common denominator, right? Because we're going to try to get rid of that fractional part. And if you can see here, just imagine when we're combining this k and this k plus 2, our common denominator is just k times k plus 2, right? So we're going to multiply by that, and k squared plus 2k, you can imagine we can factor that out. You can factor that k out because it's the greatest common factor. So we'll be left with a k times, again, k plus 2. So let's multiply that to both sides. And we can do that because of the multiplication property of equality, right? We can multiply that to both sides, and our equality still holds. So with that, let's just distribute this factor into our this other factor here. So when we multiply it by this 2 over k, the k's can cancel. So we're left with a 2 times k plus 2. Minus, by multiplying this with this fraction, the k plus 2 cancels, so we're left with a 3k times k. And on this side, this whole thing cancels out this, so we're just left with k. And then now, right, let's distribute this 2. So we have 2k, and then 2 times 2, 4, minus 3k squared is equal to k. Let's bring everything to one side, right? So we have negative 3k squared plus k plus 4, right? We brought this k over, and we canceled out this 2. And then now let's multiply by -1 because we want this factor to be positive, just so it's easier to work with, right? And we can do that because of the multiplication property of equality. So we'll have a positive 3k squared minus k minus 4, and 0 times -1 is still just 0. Now after this is a trinomial, right? So we can factor this out. So let's try to look at factors of our first term, 3, right? So 3 and 1 is really the only factors because 3 is a prime number. And then factors of 4, and just try to find a combination that works. right? And spoiler alert, it's 3k minus 4 times k plus 1. And now with this, we're going to be using that that kind of that property when there's a and b. A times b equals 0, and then a or b equals 0, or both, right? So we have this as our a, we have this as our b. So we're looking at a equals 0 or b equals 0 or both, and we solve. So we get k is equal to 4 divided by 3 and k minus 1. Does that make sense to everyone? All right. So now we're moving on to exponents, right? So for exponents, let's just first think of the definition of an exponent, right? Or what it means. So if I have a raised to the nth power, then what I'm really saying, or the question I'm asking you is, what do I get if I multiply a by itself n times, right? N times. So, and if I have a 0 or a negative exponents, well, anything, any number, any value a raised to the 0 power is just 1, right? If you have 100 raised to 0 power, it's just 1. If you have 2 raised to 0, it's just 1. And if I have negative exponent, well, I just flip that and put it in the denominator, and it becomes positive. So now a couple properties of exponents. If you have a to the power m times a to the power n, then that's the same thing as a to the power of n plus n. And you can imagine that, that's because you have a times times a, you have that m times, right, all that multiplying by a times a n times. Then if you go back to our definition of exponent, then yes, that is just a to the power of m plus n. So if you bring everything back to the definition, then it's pretty clear on how the rest of these properties kind of work, right? It's pretty clear once you just deal with these when you're trying to add up all these factors of a, and it's pretty clear that you have this m minus n for a fraction, or you have this n times n if you have another exponent, right? But after that, for these fourth and fifth ones, they're a little different, right? We kind of have this distributive property, and we can imagine that because for this first one, right, we have the factor ab times ab, right? We have that m times. If you imagine, let's separate them out into the factors of a and the factors of b. Well, that means we have a times a, m times, and then we have b times b, also m times. So it becomes a to the m times b to the m. And now, for real numbers a, which indicate the roots, right? Or if you have like a radical expression, right? So what I mean by radical, you have like a square root or a cube root or anything like that. Then we'll see later on, or I think it's the next slide, of that is equal to, the factor, the power of 1/3 or 1/2 respectively. So if you have something, right, to the power of a fraction, then always remember that it's just e over I, whoops. So I have e, my exponent, over my index right here. So okay, here we have an example, right? And the goal of this example is to try to simplify things as far as we can and write them with positive exponents, right? So again, when we're simplifying, we need to look at parentheses first. So first, deal with whatever's inside the parentheses. And we have these negative exponents. Well, let's try to write them with positive exponents. I'm going to use that factor that when you're dividing, right? If you have a to the m divided by divided by a to the n, right? Then that's just a to the power of m minus n, right? So I'm going to use that with our m's and our n's separately. So I have m to the power of 7 minus 5, right? So that's just m to the power of 12. And then I have n negative 2 minus oh wait, oops, minus 2, right, because it's squared. So that's just n to the negative fourth. And well, that's a negative, right? So I can write that in the denominator, and it becomes a positive 4. So with this, right, now let's work with that exponent on the outside, that 1/4, right? So let's distribute that to both our numerator and denominator. If you remember that property, if you have a to the m to the power of n, and that's just a to the n times n, right? So we're going to have 12 times 1/4 and 4 times 1/4. Well, that simplifies down to m cubed divided by just n to the first power, right? So moving on to radicals, it's exactly what I just mentioned, right? If n is a natural is a natural even number, then a will be positive, right? And if n is just an odd natural number, then a to the 1 over n is equal to the root, the radical, or like the fourth root or the nth root. And why is it important if n is an even number? Well, it's important because you really can't have a negative number underneath, right? So if I had like negative 8, right, to the cube root, then you can, what I'm asking here is what is a value that if I cube it, I'll get negative 8. And if you do just a little thinking, if you have negative 2 to the third power, right, so negative 2 times negative 2 times negative 2, you'll get negative 8, right? But if I had like the square root, so an even number, right, of negative 4, there is no number that I can multiply by itself that you guys know of yet that can give me a negative 4, right? So I can't have negative 2 squared, right? That's not the same because negative 2 times negative 2 is positive 4, right? So that's why it's important that a is equal to 0 if n is an even natural number. And now for the properties of radicals, well, they're actually very similar to what we had for the properties of exponents, right? Because radicals and exponents are related, because the radical is just that exponent of 1 over n. Well, so let's imagine if we have this radical, this nth root, raised to the power of n, then that just cancels it out, so it becomes n. And if you kind of look through all these, then they really kind of mimic what we have on the exponent side, except for number 2, right? Number 2 is kind of mentioned up here in our definition of a radical. And it mentions that when we take that nth root of a to the n, and n is even, we have the absolute value of a, or just kind of the reverse of this property, right? That a is positive. And one other thing to mention is that when we're simplifying a square root, right? So we have the square root of x squared. You might be tempted to just use one of these properties, right? And say that it's just x, but it's not, right? Because n is even, n is equal to 2, then it's the absolute value of x. We need to keep that in mind. Okay, so let's work with this example, right? And because we're going to multiply by the conjugate of these numbers. Sorry, the conjugate of the numerator, and we're trying to simplify this fraction. So when we multiply, right, the conjugate is you're just going to change that operation up here, right? And we're going to multiply by a fancy version of 1 by changing that operation to try to simplify things out, right? So let's use this numerator, that square root x minus 3. Our conjugate is square root of x plus 3, and let's multiply things out. Well, so we have square root of x times square root of x, so that's square root of x squared, and that'll cancel out to a positive x. And then we have this minus 3 times square root of x, and then square root of x times plus 3, those cancel out, and then minus 3 times 3 squared is just a negative 9. And for a denominator, we just kind of keep that there. And as you can see, we have an x minus 9 and an x minus 9 in the top, in the bottom. So we can cancel those out, and we're left with a 1 over square root of x plus 3. A lot simpler of a fraction. Now let's move on to functions. And so properties of functions, right? A function is like a rule. It takes inputs and gives back outputs. And if you think about it, all possible inputs of our function is called the domain, and all possible outputs is called the range. And unless otherwise noted, then let's assume that the domain of our function to be the largest set possible. And I'll be explaining what largest set possible means in a bit. So another couple more properties of functions, right? That maybe some that you're very familiar with. To evaluate a function, f of x at x equals a, you just replace any x in the expression with a. Vertical line test, we're just testing if a relation is not a function. And what it really means is we want each x value to have a unique y value, right? And we'll see a couple of examples of where relation is not a function in a bit. Now for even and odd functions, we're just looking at how they're symmetrical. An even function is symmetrical with respect to the y-axis, and this is the mathematical definition, right? Fx is the same as f negative x. And an odd function is symmetrical about the origin, or fx is equal to negative fx. Negative f of negative x. Okay, so let's try to evaluate this function, 3x to the fourth plus 6x cubed at x equals 2. Well, we just want to plug in 2 wherever we see x, so that's 3 to the 2 to the fourth, times, plus 6 times 2 to the third, so that's 3 times 16 plus 6 times 8, and that's just 48 plus 48, or just 96. And now, question here, right? Is this graph of below, is that a function? So what we need to think about is our vertical line test. And well, if we draw any vertical line across this relation, or across this graph, we can see that it intersects the graph at 2 points. Or this x value does not have a unique y value, right? So this x value, let's call it like 1. Then it has 2 y values here. I don't know, let's say like 2 and negative 2. So it is not a function. No. Now lastly, y is equal to absolute value of x. Is that even or odd, right? Well, one way to check is, let's just check what f of negative x is equal to, right? F of negative x, so we have y is equal to, equal to absolute value of negative x, and that's just x. Well, that's the definition of an even function, because f of negative x is equal to f of x. So this is even. Now for polynomial functions, right, a polynomial function is something that kind of has this form. It has, of the nth degree, right, it has these coefficients, an minus 1. We just give them indexes so we don't use up all the letters of the alphabet. And it's all of them are multiplied by x to raise to some power, right? And an is called your leading coefficient. So there are a couple properties of polynomial functions. Right, a polynomial function of degree n can have n minus 1 turning points. And if it has an even degree, right, if the graph of points has an even degree, or we have the largest exponent is called the degree. If it's even, then both ends go up or both ends go down. But if it's on degree, then one end goes up and one end goes down. And lastly, we have that if as x goes to infinity, right, as x becomes a really large number, and our graph becomes a really large number, then the leading coefficient has to be positive. And if the opposite happens, then it has to be negative. And for rational functions, it's something with the form of a polynomial px divided by a polynomial qx. And we have that qx is not equal to 0, because anytime we have something divided by 0, that just doesn't really exist. Okay. And then now for vertical asymptotes, well, if the function gets larger and larger in magnitude without bound, right? So if it goes up to kind of like infinity, and as the x value like approaches a number k, then x equals k is a vertical asymptote, or it's like a line that our function gets really, really close to, but it never actually touches. And as our y value approaches a number k, as x gets larger and larger, then y equals k is a horizontal asymptote, or the same way it's a value that our graph gets really, really close to, but never actually touches. So an easy way to find vertical asymptotes is to make the root of the denominator find the root of the denominator. And if that root does not make the numerator 0, then it is a vertical asymptote. So, let's take a look at 2 examples. So first off, what is the degree of this polynomial? Well, let's look at the leading coefficient, right? Leading coefficient is x cubed. But is it is it of degree 3? If you look at all the other factors, and it actually isn't, right? Because if we order them in terms of our largest, the term with our largest degree, we have 8x to the 7th as our largest, plus x cubed, plus 5x squared, plus 3. So I was trying to trick you guys there a little, but if you order it with respect to the largest degree, then you'll see that this polynomial is of degree 7. And now, let's find any vertical or horizontal asymptotes and holes if we have any of them, right? So one of the things is when you see polynomials, it'll be pretty beneficial to try to factor them out. Let's factor out this bottom, this denominator, and I'll factor out the numerator. So we have a1, right? So we just have some x's here. And let's find factors that multiply up to -6 that add up to minus x, right? So if you do a little thinking, you'll find that -3 and +2 do the job, right? And for our numerator, we have, again, a equals 1, so we have x, and factors of -3 that add up to -2. Well, we have -3 and +1, right? So now let's find some vertical asymptotes. Um, vertical asymptotes, we have, let's set the denominator equal to 0. So we have x minus 3 equals 0. So x equals 3. And then we have x plus 2 equals 0. So x equals -2, right? So with this, let's check if it makes any of our numerators equal to 0. Well, if we plug in x equals 3 into our numerator, we see that'll make this factor 0. So this is not a vertical or horizontal asymptote, it's a hole. And then for x equals -2, if we plug that into our numerator, we don't get 0. So this is a vertical asymptote. And now let's try to imagine for a horizontal asymptote, right? So as our x gets bigger and bigger and bigger, and our x increases, then we can kind of imagine that these x squared values, they grow a lot faster than the other values, right? So we have x squared minus 2x minus 3 over x squared minus x minus 6. We can kind of imagine, right, as x goes to infinity, that these values grow and grow and they kind of take over, right? They kind of take over because they're now the largest factor, right? So then at x equals infinity, so sorry, as x goes to infinity or some really large number, and we will cancel this out to 1, right? So as we can see, y equals 1 is a horizontal asymptote. Now for exponential functions, this is really just using our definition of an exponent and returning it into a function. So f of x is equal to a to the power of x. And there are a couple of extra properties there. Now logarithmic functions, so a lot of times for students, I phrase it in terms of a question, right? So the question that an exponential equation asks us, or exponential function, it says, if I give you a value y, right, and you raise it to some power, so a to the power of y, what do I get, right? What's my value x? But what a logarithmic function asks you is, here's my base, right? My base a, and here's my answer x. What power do I have to raise it by in order to get that x, right, or this y? So there's a couple terms, right? We have a base of a for logarithmic functions, and yeah, so you have a couple of these other properties of logarithms, and if you just kind of think about them, right, at first glance they look kind of random, but really quickly you can see that they're related to the properties of exponents, right? So if you can imagine, just kind of think through the definition of a logarithm, and you'll see that they're actually connected. Okay, now a couple more theorems or laws with logarithms. So we have this change of base theorem. So if x is a positive number and a and b are positive real numbers, right? And you have this log a, then you can separate them into log base b x and log base b a. and you have to make sure that a and b are not the same number. So for any positive number, a and x, and a doesn't equal 1, right? Because if, oh, does it not mention that? Oh, okay, yeah, it's one of the properties here. If you have log base a of 1, then that's equal to 0. And why is that? Well, let's think about that. Because the question it's actually asking is, I have the base a raised it to the power 0 equals 1, right? So that makes sense. However, we can never have 0 in the denominator, so we need to make sure that that is not 0. So we need to make sure that a is not 1. And now change of base formula for exponentials. If you have a to the x, then you can also raise that from, you could also make that equal to e to the power of ln a times x. Because, and why is that, right? So let's think about it. Remember the properties of exponents, we can separate out, right? So that's ln a power of x times, it'll raise to the power of x. Now imagine the change of base formula for exponents here, and that just equals a, so we still just have a to the x. So a couple of examples. Oops, looks like I forgot parentheses here. So let's expand this, right? So first, that property of logarithms, let's separate that fraction. So we have the natural log of x cubed e to the 5x fourth plus 3x. Oh, whoops, 3x is up here at the top. Plus 3x minus ln of 9x to the fifth 1/2. Oh no, running out of space. 1/2 times 7 to the 1 over x. Okay, so then we can separate that with, because they're multiplied by each other, so we can have ln x cubed plus ln e to the 5x to the fourth plus 3x minus ln times 9x to the fifth minus, right, because I distribute that negative, ln 7 to the 1 over x. And then if you look at those properties of logarithms, I can bring out this exponents, right, to multiply by a coefficient in the front. So I have 3 ln x. I'm going to bring this out, right? So plus 5x to the fourth plus 3x. And now ln, right, natural log, is just log base e. So I have log base e to the e, that's just 1, right? So times 1. Then I can actually separate this further, right? To where I have, I'll write down here, I have minus natural log of 9, and minus, I'll bring out the 5, so 5 natural log of x. And lastly, minus 1 over x natural log 7, right? So all this looks pretty complicated, but we were able to simplify it down into something like this, right, which is a little easier to work with. And now let's take a look at this example here, because it works with both exponents and logarithms. So for here, we're solving the equation 3 to the 2x is equal to 4 to the x plus 1 power. So first, let's take the logarithms of both sides, and we can keep this equal sign because we're doing the same operation to both sides, right? So then I bring out this 2x to the front, so 2x times natural log of 3. Bring out this x plus 1 to the front, I have x plus 1 times natural log to the 4. And now let's just imagine bringing out that x, right, because we're multiplying it. So I'll take all the other factors times x, and same thing here, I'll separate that x. Now I'll isolate my x and I'll bring it all to one side. So I'll bring this ln 4x to the other side, and then factor out an x, right? This x, I'll factor it out. Then I divide both sides by this, which is just a big number, and I'm left with that. All right. So now we're moving on to the derivatives, right? Or we're just really looking at limits and definition of continuity. So limit of a function. Well, the limit of the function, what it's asking you is, we have this function f of x, right? And I'm looking at the limit as x approaches a. And a lot of times, right, you can just really plug in a for x and evaluate it like f of a. But there are a couple of times where we have discontinuities, right? And for example, you can have like a hole. So as x approaches a, or as x gets really, really, really close to a, it looks like it's going to this value here, right? But let's say f of a is actually up here, and that's actually just um, that's one example of why limits is important, right? So limits tells us the behavior of function as we get really, really close to a value, and a lot of times we don't really even care, or sometimes we might not even know what the actual function at that value is, right? We actually might not know what f of a is, but we can know the limits. So existence of limits, well, sometimes the limit may not exist, right? If a limit goes to positive infinity or negative infinity, then technically that doesn't exist, right? Because infinity and positive infinity are not a number. However, it's a better answer to give infinity and negative infinity and not just does not exist because as mathematicians, we're scientists, so we like information. So any answer that can give us more information is better. So telling me the limit does not exist, that doesn't give me a lot of information, right? But telling me it goes to infinity or negative infinity, that gives me one more piece of information because I know my function gets very, very large, or it gets very, very large but negative. And if f of x becomes infinitely large in magnitude, positive, as x approaches a from one side, and it goes infinitely large in magnitude as x approaches a from the negative side, then the limit does not exist. And what is that talking about? It's talking about cases where you have this like a vertical asymptote, right? So from one side, your function goes to positive infinity, and from the other side, it goes to negative infinity. So it really doesn't go to positive or negative infinity, right? It just does not exist. And then lastly, this is kind of what this second one was saying. But there are a couple other cases where this will be useful. So we're looking at the left limit, or when x approaches a from the left, or when x approaches a from the right. And if those two are not equal, then our limit does not exist. So here are other couple of rules that I wanted to mention. And one of the quick things I just wanted to mention is that you can distribute a limit, right? I feel like that's one of the more important ones. Well, not really distribute, but you can evaluate a limit in different steps, right? So if you have like a function f of x plus or minus g of x, we can separate that to the limit. And same thing with multiply or division or raise to the exponents. You can kind of distribute, quote unquote, that limit into the function, okay? All right, so now limits at infinity. Oh, does someone have a question?
I was just gonna ask, are you doing another session later?
I do not believe so.
Okay.
However, in just a little bit, we're going to split up into groups, and then we're going to work through a couple practice problems. So, I mean, if you wanted to leave and come back, you could still get some information from that.
Okay.
Cool, cool. All right. So, okay, cool. So limits at infinity, and what that question's kind of asking you is, as my x approaches infinity or negative infinity, so as x gets to a really, really large positive number, or really, really large negative number, what happens to my function, right? So what we're really kind of focusing at, we're focusing at those rational expressions, those rational functions. So something that has polynomial px divided by polynomial qx, right? Where it doesn't really exist. So one way to find these limits at infinity is we're going to divide px and qx by the highest power of x in our denominator qx, okay? And after that, we'll use the rules of limits and look at the rules for limits at infinity. If we have like a 1 over x to the n and x going to infinity or negative infinity, then that equals 0, right? Because that's 1 divided by some large, large number which approaches 0, right? So if I give you like 1 over like a million, right? And that's like 0.00000, 1, really, really close to 0. Okay, and these correspond to our horizontal asymptotes. So here's a quick example, right? So in this first one, if we just substitute in, right? That's always the first thing you should try. Just substitute it in and see if it works. So if we plug in x equals 4, our denominator comes 4 minus 4, becomes 0, and we can't have that. So let's try to factor it out. And at first glance, there's really not, it doesn't look like we can factor much out, right? But what we can do is we can multiply by a conjugate. So we can multiply x minus 2 and x minus 4. We can multiply by that fancy version of 1, square root of x plus 2, square root of x plus 1. So in the numerator, we'll have x, right? Because x square root of x squared, x, minus 4, then x minus 4, plus 2, square root of x plus 2. These two can cancel. So I have the limit as x approaches 4, 1 over square root of x plus 2. And that, if I now want to just plug in that 4 wherever I have x, I just get 1 over square root of 4 is 2. So 2 plus 2, 1 over 4. And now this is one of those limits at infinity. So we're going to try to see if we have a horizontal asymptote here. So what do we need to do? Well, let's look for the highest degree or highest power in our denominator and divide both polynomials by that. Well, we just have x to the 1, so we're going to divide both numerator and denominator by x, which if you think about it, we're kind of multiplying again by just a fancy version of 1. So I'm going to distribute that 1 over x. So I have 8 times 1 over x. Those x's cancel, I just have 8. Then 2 times 1 over x, which is just 2 over x. Then I have 3x times 1 over x. X's cancel, I have 3. Plus 9 times 1 over x, 9 over x, right? And then with this, let's look at those limits again, right? We can split them up, right? But just to kind of save space, let's just think about it, right? So limit as x goes to infinity of 8 and also of 3, right? There's no x in that term, so nothing really happens. But for this 2 over x, well, what do I have? I have 2 divided by some really, really large number because x is going to infinity. So that goes to 0. And this 9 over x, right? X goes to infinity, goes to 0. So I'm just left with an 8 over 3. 8 over 3. Cool. And Peyton, I just remembered, I did want to mention that all this is being recorded, and you can find it on the UTD SSC peer tutoring channel. And from there, you can kind of rewatch this whole thing. I'm sorry, I just kind of forgot at the spur of the moment. But yes, this will be recorded. This is recorded right now. Okay, and lastly, what are the last topic? So let's look at continuity. And for continuity, we just have 3 conditions that we need to make sure happen, right? And we can really, in my opinion, you only need to like memorize this one, right? What you need to make sure is that this part exists, this part exists, and they're equal to each other, right? And if any of those fail, right? If one side doesn't exist, or if both doesn't exist, or if they both exist but they're not equal, then the function is discontinuous. And then now, if something's continuous on a closed interval, right? So we know something's continuous on an open interval, right? Because like the values of limits, and we can find that, right? But we need to make sure if it's continuous on a closed interval, make sure it's continuous from the right on x of a. So you need to make sure that limit as x approaches a from the right is equal to f of a, and the limit as x approaches b from the left of f of x is equal to f of b. So that's the only difference there. We're only looking at these one-sided limits for a closed interval. So here's an example, right? Are these functions continuous? Well, let's check, right? And we're just going to check by the graph. So it looks like our limit as x approaches 3 for this first one, it looks like our limit exists, right? We can get really, really close to 3, and it looks like we're ending with like about a 2, right? So our limit exists. But at that spot, we have a hole. So our f of 3, oh, okay, come on, work with me. Our f of 3 doesn't exist. Okay, looks like my computer's glitching up. And then lastly, for this last one, we have the limit from the left, it looks like it's approaching -1. The limit from the right approaches 1, right? So our left and right, I guess is going 0. Our left and right limits do not equal. So our limit does not exist. So again, it's discontinuous, right? And lastly, you can go over these on your own, but what it's really just talking about is these common types of functions and where they are continuous, right? So I'll just go over a couple of I'll just go over them really quickly. Polynomial functions are continuous everywhere, right? If it looks like a polynomial, they're good. Rational functions, they're continuous everywhere except x's that make our denominator equal to 0, right? Those are our vertical asymptotes. And now a square root function, we need to make sure that the inside is positive, right? Because square root, that 2 is an even number. And exponential functions are continuous everywhere, and logarithmic functions are continuous on all positive x's. Okay. So we have this last quick example, right? So let's find the value of x's where this function is discontinuous, right? So let's when they give you a piecewise functions, most of the time they're going to be looking at they're going to be kind of testing whether you can like evaluate limits and whether you know that as x approaches c, f of x, if that is equal to f of c, right? So let's just look at that, right? So as our limit, and also to give you piecewise functions, you're also going to be looking at the left and right limits. So let's look at x equals 1. So as x approaches 1 from the left, right, then we have x plus 1 as our function. And we hope that that's equal to x approaches 1 from the right. But with that, we have this function, x squared, minus 3x plus 4. So to evaluate this, let's just plug in the limit value. So I have 1 plus 1 here, 2. And I have 1 minus 3 plus 4, and that's equal to 2. So we're good, right? And lastly, to check. So we know that our limit exists. Now let's check f of 2. F of 1. F of 1, right? And f of 1, I have to use this expression because here it's where x is greater than or equal to 1. So I'm going to have 1 squared minus 3 times 1 plus 4. That again is equal to 2. So we have that limit exists and it's equal to the value of our function. So x equals 1, continuous. And now x equals 3, right? So I have the limit as x goes to 3 from the left. We have to use this function. So I have x squared minus 3x plus 4. We hope that that's equal to the limit x approaches 3 from the right of 5 minus x. So let's just plug in my 3 here. I'll have 3 squared minus 3 plus 4. And then here I'll have 5 minus 3. And let's see, are these equal? Well, here I have 9 minus 9, so 0. So you just have a 4. And 5 minus 3, 2. These are not equal. So our left and our right limits do not equal. So our limit itself does not exist. So x equals 3 is discontinuous. All right. Cool. So right now we'll take a quick break and then we'll come back and we'll work out some problems in small groups. So let's be back in, have a 5-minute break. So let's be back at 12:05. All right, Peyton, it looks like you're the only one that saved for the practice questions. And I mean that's all good. We'll keep on working. So right now I am actually going to stop sharing my screen and Shriman's actually going to take over for these practice problems. And then, yeah, I'll just be here as backup.
Okay, let me go ahead and get the stuff shared. I downloaded them earlier, so shouldn't take too long. Let's see. Let's see, got it. You guys can hear me fine, right?
Yep, I can hear you.
Okay, sounds good. Let's see, did it finish up? Share files. There we go. So you guys can see the practice problems PDF that I just shared now, right? Assuming you can. Okay, so let me zoom in a little bit. So the first one is simplify the following expression. So, Peyton, if you can hear me, do you have any ideas on how to get started with this, or do you want me to just start working it out? I guess I will just start working it out. So the first thing is you want to sort of follow order of operations on these. So the way I like to do it is I like to just evaluate all the parentheses first, and then do the multiplication, and then exponents and multiplication division, and go from there. So I will rewrite this as -4 squared minus, and like for this first set of parentheses, there's not really anything to evaluate, so we'll just leave it as like -2 cubed. We still have to deal with the exponent, but we'll do that in the next step. And then we have 4 times 6 minus 7. So the 6 minus 7 evaluates to a -1. So we want to rewrite that as plus 4 minus 1 squared. So done with the top part. It was pretty smooth. Let's look at the bottom part. So no parentheses on the first term. And then here you have parentheses. You have 4 minus 2, which is a 2. So you're just going to get -8 and parentheses 2 cubed. And we're going to have minus, and then this -1, there's nothing to evaluate, so that's just -1 to the 4th. So I guess for the second step now we want to do all the exponents. So you have to be a little careful with these because there's a difference between having -4 squared and having parentheses -4 squared. So you don't want to mix those up and just say, oh, this is the first one is 16. The first one is 4 squared times like -1. Well, the second one is like -4 times -4, which is 16. So this should evaluate to -16. You don't want to accidentally make that mistake. And then this -2 cubed will evaluate to a -8. But since you have a subtraction sign in front, the subtraction negative cancel out and it becomes addition. So you get like a +8. And I guess this -1 squared is fairly easy. It's just going to be 1 and plus 4 divided by, you're going to have 6 squared, which is 36. And then 2 cubed is 8. 8 times -8 is like -64. And then finally, this -1 to the power of 4, that's like any -1 to any even power is going to give you +1, and -1 to any odd power is going to give you -1. So since 4 is even, you're going to get +1, but since there's a subtraction sign in front, it's going to be -1. So this turned out pretty easy. So the top part, -16 plus 8 is -8, plus 4 is -4. And then 36 minus 64, let's see, what is that going to be? So it's going to be like 28, minus 28 if I'm not mistaken. Yeah, it should be minus 28, yeah. Because, yeah, it's minus 28. And then you have another -1. So that should be -4 over minus 29, which is also equal to 4 over 29. So anyone have questions on this one, or is this one easy enough? Assuming easy enough? Okay, I'll take your, okay, I'll assume it's easy enough. Let's see, so this next one is, so, okay, I guess we can do both. Unless, if you have any like specific picks on what question you want me to work out, I can skip to those, but if not, I will just go in order, I guess. So this x plus 2 squared, Nico covered this in his presentation. Like it's almost like the a plus b whole squared formula, but I'll work it out manually just in case anyone forgot. So it's x plus 2 times x plus 2. Let me write it on this side so I don't run out of space. So when you multiply these, this x multiplies to both terms, and you have this multiplied to both terms, and finally you multiply the 2 here, and you also multiply it here. So you can call this foiling. You can do the foiling method, which is like you multiply the first terms, then the outer, then the inner, and last. But the thing about foiling is it only works for binomial times binomial, really. But if you do this form, it like works more generally for any case. So I prefer using this nowadays. So the x times x is going to give you x squared. The 2 times x will give you 2x, so plus 2x. The other 2 times x will give you another 2x. And the 2 times 2 will give you 4. So you can combine like terms and make this x squared plus 4x plus 4, which isn't too bad. And then, now earlier I was saying you should not, foiling isn't very good for bigger examples, and we'll see why that is now, because we're going to do 3x minus 7 times that x squared plus 4x plus 4. And if you observe carefully on this one, I'm almost like following PIMDAS in a way, because like I dealt with the exponent first, and then I'm multiplying this other term into it. So you should always evaluate exponents for some of these. So you're gonna want to multiply in the same way I was showing earlier. You want to do the first term here, then you want to go here, then you want to go here, then you want to take the second term and go to all three, and you want to like sum up all of those results. So 3x times x squared is 3x cubed. 3x times 4x is plus 12x squared. And then 3x times 4 is plus 12x. And then you have like a minus 7 times x squared, which is a minus 7x squared. Minus 7 times 4x is minus 28x. And finally, minus 7 times positive 4 is minus 28. So, and it kind of makes sense. We're really only expecting like one constant term, right? And we got one constant term, so I would assume we're doing this right, but let's just combine all the like terms now. So if you look at it, we only have one x cubed term, so we can't really change that in any way. But we have two x squared terms. We have 12x squared and we have minus 7x squared, and you can actually subtract those, so it's going to give you 5x squared, because it's almost like, if you don't believe it, you can just do it like, okay, let me switch to a slightly less thick marker, or I guess pen on here, so I don't take up as much space. That's pretty low, right? Okay, here. So this, so if you have like 12x squared minus 5x minus 7x squared, you can almost just like factor out the x squareds, so you just get like 12 minus 7, which should just be 5. So that's just equal to 5x squared, because 12 minus 7 is 5. So if you don't believe it, that's more of a, I guess, like a way you can actually like see that it's true. So we had 3x cubed, and then we have plus 5x squared. And then 12x minus 28x, so let's do 12 minus 28, which is minus 16. And I know, like, here I'm doing it in my head, but on your exam, I would highly recommend you do it on paper, because you don't want to lose easy points like that. So we got a minus 16x right here, and we have a minus 28. And this is our final answer for number 2, expanding the expression. I would probably have chosen to type it, but I can't really do exponents without using like the caret symbol, so I'll just draw these. Okay, so this one is not too bad of a problem also. You just want to factor out the biggest like exponent term, like the biggest common term. So we can either take this, like the first thing, there's like numbers we can factor out, and there's also like x terms we can factor out. I want to just factor out like the x terms first, and then we'll look at the numbers, so we can go more step by step. So we have to look through all of the terms and see what's the biggest x to the power of some number, or the smallest. We look for the smallest because you have to be able to take it out from each term. So the smallest one I'm seeing is an x squared. Okay, and that should just leave you with 3, and then if you take out x squared from x to the 6th, that's like dividing x to the 6th by x squared, right? And that should give you x to the 4th. And if you remembered in Nico's slides earlier, you went over that also. So 3x to the 4th, and then the second one's going to be minus 24x squared. Same idea, x to the 4th divided by x squared will just be x squared. And finally, x squared divided by x squared is 1. So this is plus 48. So now let's look for the biggest number we can factor out. And if you think about it, you can like come up with like, immediately you can like come up with a bound on your biggest number that you can factor out, because, or the smallest number that you can factor out, because it has to be 3 or below, right? Because if you want to factor out a 4, you can't pull a 4 out from, like, you can't pull any number that's bigger than 3 out of a 3. So like 3 is the maximum you can do, and if you look at it, 3 actually works. But suppose like you had I don't know, you had some other value that didn't like work with a 3, then you would have to check smaller values. But here, the 3 factors out, so just give us 3x squared now. And then we have a 3 gone, so 3 divided by 3 is 1, so all we have is x to the 4th on the first term. And then we have a minus 8x squared on the second term. And finally we have a plus 16 on the third term. So there we go. So if you remember, so like this, if this x to the fourth idea is a little like weird to you because you're normally used to dealing with if you're normally used to dealing with x squareds in your quadratics, there's a little trick I like to use. It's like sort of setting like y equal to x squared and rewriting your entire expression. So that would make it like 3y, and then you would have like, so like if y equals x squared, then like y squared equals x to the fourth, so you get like y squared minus 8y plus 16. And now this is like an easy quadratic to factor, and you can just rewrite that as like y minus 4 whole squared dot 3y. So we can do that, or and then like you would just plug your x squareds back into the y, so you just get 3x squared times x squared minus 4 whole squared, and that'll factor out. But if that's a little weird or excessive for you guys, I would just say, okay, so you know that like when you have an x squared, you're having x and x, but so when we have x to the fourth, we're probably gonna have x squared and x squared. So you should just like look at it and be able to see, okay, x squared minus 4 and whole square of that. And if the so if you're like a little rusty on these factorizations, I would suggest you guys look through like factoring methods. There's like two popular ones that I know of. It's like the AC method and it's like the X method or something. I don't know what the other one's called. I normally use the AC method. It works really well with basically anything I've encountered so far, so I just always use that one. So next page it is. Okay, so we're getting to some rationals. So remember, we should always like follow the order of operation. So multiplication division comes before addition, of course. So let's just sort of like put some parentheses so we don't forget. We're gonna do this, and then we're gonna do with the addition. And if you look at this, you have like a rational function divided by another rational function. So if we want to get it to like multiplication type terms, so the way to do that is to flip the second one. So you're gonna have like x to the fourth minus 16 over x squared plus 4. So the first one stays the same, but we want it to be multiplication instead of division. So when we change it to multiplication, we flip the second fraction. So you're gonna have x cubed plus 4x on the top, and you're gonna have x squared plus 3x plus 7 on the bottom. And remember, we'll deal with the addition after, so don't worry about that too much yet. So not too bad. We can just pull out an x real quick from this part, right? So it'll just be x times x squared plus 4, and look at that. We have an x squared plus 4 in our denominator also. So this cancels with this. And let's factor up this one, see if we can make anything happen. So let's see, can we factor this? We can do, so if you think about it, the numbers have to multiply to 7, and they have to add to the middle b term. But you know, I'm not immediately seeing something for x squared plus 3x plus 7. So that makes me think, okay, let's use the discriminant formula just to make sure we didn't accidentally miss something. So we're gonna do b squared, so the b value is 3, so it's like 9. Oh, it's yeah, and then minus 4ac, so it's minus 4. The a value is a 1, and the c value is 7. And if you look at that, that's definitely a negative value, right? So when you're less than 0, that means you don't have factors. So this x squared plus 3x plus 7 term is not getting factored. We can guarantee that. So yeah, so if you're ever not sure if it can factor, just use that b squared minus 4ac. If it's equal to 0, that's like you have one factor whole squared. It's like if you have x minus 2 whole squared. If it's greater than 0, that means you have two distinct factors. And if it's less than 0, that means it's like, technically they're called like, you're going to have like imaginary values for your factors, but we'll just say they don't exist for now. So you're going to have, so we have an x left on the numerator, so we're just going to multiply that x into the second part. So it's going to be x to the fifth minus 16x. And look at that. We have x squared plus 3x plus 7. And we can also add, you guys can still hear me, right? Okay, yeah. And then it's going to be plus 16x over x squared plus 3x plus 7. So now we're adding the second part that we said we'll deal with later. And since we already have a common denominator, we can just directly add. So it's just going to be x squared plus 3x plus 7 over, and minus 16x plus 16x is just 0. So all we have on the top is x to the fifth. And this is a simplified expression. Came out nice and pretty neat, I would say. Okay, let's go to the next page. Okay, let me zoom in a bit. So this is asking solve the following equations, and these are all linear systems. So the way you want to do this is you want to multiply all the x values out. You want to isolate the x's and isolate the normal terms and see what happens. Okay, 1 second. Okay, so let's go ahead and start this one. So let's just multiply out this 9 into the parentheses. So we're just going to get 36x. Oh, I guess here I'll just type it out since there's no exponents, right? So when you multiply that 9 into the parentheses, you're just going to get like 36x minus, you're going to have 9 times 7, which is 63. And then you're going to have a plus 4x still, which all equals 3 times, we're going to multiply 3 into the parentheses. So it's going to be 3x, and then you're going to multiply the 3 times 2, which is a 6. You're going to have a plus 5. So this is just going to be pretty easy to deal with now. 36x plus 4x is just 40x. And then we're going to bring the 3x to the other side, so it's going to be minus 3x. And we're going to add the 63 on both sides, so you're just going to get equals 11 plus 63. And works out pretty well. So the left side is going to be 37x. And the right side is going to be 64, 74x. Or 74, my bad.
There's
74.
nothing showing up on the screen.
Is it not showing up?
Okay, there it is.
Okay, yeah, I think the text might be a little slow sometimes. It takes a few seconds.
Okay.
Okay, so you see it now, right?
Yes.
Okay, yeah, sounds good. So, and then from here, we just divide by 10 on both sides, so you just get x equals 2. And that is our answer for number 5. Let's go step by step, and it should all work out. So the second one is not too bad either, but we're going to have a quadratic on this one if you look carefully, because we have an x times x on the left side. So let's see how this turns out. And normally with quadratics, the way I would say is the best way to go about it is you want to make one side equal to 0 and bring all your other terms to the other side. And then you want to factor that quadratic you get and set the factors equal to 0 and you just solve for it. So let's go ahead and get started on this. So first one, you're going to get x times x minus 10 times x. So x squared minus 10x equals 4 times 8, which is 32, minus 4 times x, which is minus 4x, so minus 41. So the way I like to do it is I like to make sure my x squared term is positive. So I'm going to leave my x squared term on my minus 10x on the left side. I'm going to bring everything else to the left side. So let's first bring this minus 4. So before we get going, this 32 minus 41, you can just simplify all of that to, so this and this, just get rid of all of this, and just 32 minus 41 is just minus 9, right? So we're just going to have it like this, so we don't need to deal with two terms moving. So we'll add the 4x and the 9 to the other side, so you're going to get x squared, and then minus 10x plus 4x is minus 6x. And this minus 9, when you add it to both sides, you're just going to get plus 9. It's all going to be equal to 0. This works out pretty nice because this is just x minus 3 whole squared, which is equal to 0. So you know that x equals 3. It's your only value. And, just plug in to check. Doesn't hurt. So 3, and then 3 minus 10 is minus 7, equals 4 times 8 minus 3, which is 5. So 4 times 5 is 20, minus 41. So that's just minus 21 equals minus 21. So that's good. So we know we did this right. So if you're ever not confident, or if you have some extra time on your test, just go back and plug in and make sure you didn't make some small computation error. So let's see, next page. Okay, so this right here is a polar function, but we don't need to find out what the polar function is or anything. So all we really have to do is figure out if it's a function or not. And Nico, on his slides, he showed you guys the circle, and he showed that like it's to -2, and here it should be like if you have two y values for one line. If you draw a vertical line and it intersects at two different points, you failed the vertical line test. And if you fail that test, that essentially means you're not a function. So we can just draw a vertical line anywhere, see what happens. Just draw it right here, and look, we failed. There's 2 points, and you just have to so this one's really easy to tell that the vertical line test is going to fail. I don't know if you get, normally it's not too difficult to see. You just have to look through the graph and see if you can draw a line where you get 2 points. And I guess the one way I'm assuming they can maybe trick you or something is if they do something like this and they just put a random point also for the function. And if you draw something like this, you still get 2-point intersection, so it's not a vertical line test. So it's not a function. But if you draw anywhere else, you pass. So you just have to watch out for stuff like that. But I don't think they'll get that tricky. So this is not a function. So I'm going to type text. It might take a second for it to show up. Not a function. So let's go to the next question. So answer the following questions using the function. Find the domain. So the domain is actually really easy to find in these. All you have to do, so the only time, okay, so first let's sort of, okay, so the only time the domain ever doesn't really exist, or if there's an issue, is when the denominator is equal to 0, right? Or else it's always going to be defined. So let's set this denominator equal to 0. So it's going to be x plus 1 times x plus 3. And since we're already in the factoring mode, let's just factor the numerator also. So the numerator, when you factor, is just going to be like, it's going to be x plus 3, x minus, no, it's other way. It's going to be x minus 3, x plus 2, yeah. X minus 3, x plus 2. So essentially, if you have like two of the same factors on the top and bottom and you cancel out, you can make it a whole. But in this case, we don't have any of the two same factors because we have an x minus 3 and an x plus 3. They're not the same, so you can't just cancel them out. But suppose the top one was an x plus 3, then you could cancel them out and it would be a whole. But if they don't cancel out, then these denominators actually become asymptotes, which is, well, too bad. So the domain for this, let's write it in interval notation because assuming that's what you guys use mainly, that's what I always use. So we're going to start from negative infinity, that's high enough, and we're going to go all the way to negative 1. And the key aspect is this x equals negative 1 is an asymptote. That means that you cannot like ever touch that asymptote, so we're going to keep it as an open bracket. And then we're going to do union. And now we look at the second part, which is between, oh wait, my bad. So the first asymptote you actually reach is x plus 3, right? Because that's negative 3. So we're going to want to make that a negative 3. And it's the same idea. And then the second, and we do union, and we start at negative 3 on the right bit. So we're going to make it open bracket still. So negative 3. And we go until negative 1, right? Because it's the other asymptote. But again, at negative 1, there's an issue. You can't touch it. It's an asymptote. So we're just going to put another set of this. So make it like that. Open bracket. And then we're going to do union. We're going to go from negative 1 right side of it to infinity. And it's infinity. That is our domain. So we're only undefined at negative 3 and negative 1. Now for so just to make sure you guys can see what I'm typing, right? Okay, yeah. The typing might have a delay by like a 5-second delay. I don't know why the typing takes so long to show up. Normally, I was teaching online also happened, but okay, yeah. So now it says find the x-intercept. So an x-intercept is when you cross the x-axis. That's when your y value is 0. So for those, we just had to set the numerator equal to 0, and lucky for us, we already factored the numerator. So x minus 3 equals 0, we know that x equals 3, and for x plus 2 equals 0, we know that x equals negative 2. So there we go, and yep, we got that done, and I think there's more parts on this. So it says find the y-intercept. So the y-intercept, if you think about it, that's when your x is a 0. So let's go back here and just plug in 0 x values. So we're going to have minus 3 times positive 2, which is minus 6, divided by 1 times 3, which is positive 3, so it's minus 2. So it's just, I guess we can say it's just, so y-intercept is like, I don't know, y of 0 equals, would be good. I think we got minus 2. Let me just double check to make sure I'm not typing the wrong thing or writing the wrong thing. So minus 3 times 2, minus 6, and then 1 times 3 is 3. So yeah, minus 6 over 3 is minus 2, and I think I wrote a minus 2. Yep, so we're good on this. So find the vertical asymptotes, and if you remember, we had x plus 3 and x plus 1, right? So the vertical asymptotes are, this is the denominator, they're just x equals -3, because you have to set it equal to 0 and solve for x, right? So x equals -3, and x equals -1. Not too bad. And finally, for the final horizontal asymptotes, so this isn't too bad either. I don't know if you remember this, but there's like 3 cases. There's bigger on the top, bigger on the bottom, and equal exponents. And in this case right here, we have equal exponents because like we have x squared for the highest on the top and bottom. So that means we just divide the coefficients, which is just 1 over 1. So horizontal asymptote is y equals, because squared 1 over 1x squared equals 1. So does f of x have a hole? So I already mentioned holes earlier, and you get a hole cancel out on the numerator and denominator. And in this case, you cannot. So no hole. Yep. Okay, so next page. Okay, so simplify the following expression. So not too bad either. So we have 2 options. We can either just bring this entirely down and just make that a positive one for like the parentheses exponent part, or we can just distribute that negative into all of these and just deal with them. I want to do the distributing. I think it's a little nicer, so we're gonna have actually, you know what? No, I want to bring it down because you're going to have to do 2 to the -1. I don't want that to be confusing for anyone. So yeah, z to the 7. We're just going to have this 4x squared y cubed z to the -3. And then we're just going to have this second part, 2x to the 4th, y to the -2. We're going to have a positive 1 now. Alright, so not too bad. So, and the reason it became a positive 1 is because we took the -1 and we went down, so it becomes positive. So this is just going to be, for this part, just going to be 2x to the 4th. So we're just looking at the denominator right now, and y to the -2. And for this part, you're going to have 4x squared, y cubed, and you're going to have z to the -3. So if you think about it, so when you multiply exponents, you add. So like x squared times 2x to the 4th. Is there something? Oh, I thought that was just Outlook giving this noise. Okay, so let's deal with the x's first. So 4x squared times 2x to the 4th, that's just 8x to the 6th. 8x to the 6th. And y cubed times y to the -2 is just y. And z to the -3 says z to the -3 over z to the 7th, and we can just bring the z up, right, and make it a positive exponent. So that's just going to be z to the 7th dot z cubed, which is just z to the 10th. So all you're going to have is just z to the 10th over 8x to the 6th y. Not too bad, I would say. And for this one, so this is rationalization, and we're running out of time. I just want to look through and see if I see any other hard ones to look at before. Okay, I want to do a log one and the exponential solving also. So let's see. Okay, so yeah, so we're gonna I'll just give a brief overview of 11, and then I'll move on to the other ones because it's going to take some time to write out for me. So essentially what you're going to do is you're going to multiply by the conjugate on the top and bottom. So you're going to just multiply by root 2x plus root 2x plus h on the top and bottom, okay? And you do that to here, and you do that down there, multiply, and then you see what happens, and you simplify. It shouldn't be too bad. Because basically a minus b times a plus b is a squared minus b squared, and since you have square roots, the square roots go away, so it actually comes out really nice, which is also why conjugates are very popular with square roots. So I'll go to the next question because it's going to take me some time to write out. So here we have this solve the following equation. So on these you want to get the same basis and set that exponents equal to each other. So if you look at this, we can convert this 9 to base 3, which would make it 3 squared. So we're going to have 3 8x plus 5 equals 3 squared. So squared times 3x, which is 6x. So 2 times 3 is 6x. 2 times 3x is 6x. So now we just set these exponents equal. So you just have 8x plus 5 equals 6x. So you just get 2x equals negative 5. We just move the 5 to the other side, 6 to the other side, and you get x equals negative 5 over 2. So not too bad, I would say. And if you guys actually want to know why this works, you can, once you have it like this, you can take like log base 3 on both sides, and the logs cancel out, and then you just have 8. And then by log rows, you can bring it back. But, oh, well, this is awkward. The last student left. Okay. Well, let's see. So, let's keep going for the recording. So here we have, to simplify this log, so essentially when logs are added, you multiply them and you combine. And when logs are subtracted, you divide when you combine. So, let's see how we should do this. So let's just start from left to right. So we're gonna divide the two first. So first I want to just like get rid of all of these like coefficients, and you can do that by just bringing them back and making them exponents. Not too bad. So it's just going to be ln 7x minus 3 equals, oh, not equals, my bad. That should not be, that should be a subtraction sign. Minus ln 3 minus 7x. And you're going to also have a, you're going to have the 1/2 become square root, so you're just going to have, and this is also like squared inside, so I'm going to write that. That's the entire point of this. And then you're also going to have like plus ln, and you're going to just have like square root of 4x, and that's like 4 square root x, or 2 square root x if you want to write that, but I'll leave it like this. And if you think about it, let's see if we can rewrite 7x minus 3 a little bit. So 7x minus 3, if we pull out a negative, so if you just factor out a negative, it will give us like 3 minus 7x, and we also just have a negative on the front. So that might be a little helpful with this. So now let's just do the division part real quick. So this is also just minus 3 minus 7x. So you're going to have a big ln of minus 3 minus 7x divided by 3 minus 7x whole squared. Easy enough. This cancels out. This goes away because they're the same. That's kind of why I rewrote it. And we also just have plus ln square root 4x. And this is multiplied, so we're just going to get a final answer of ln minus square root 4x divided by 3 minus 7x. Shouldn't be too bad, yeah. Let me just make sure I didn't. Let me just double check my work and make sure I didn't make any mental calculation error on this one. Let's see. Okay, yeah, it should be okay. Yeah, so I think the key has it like so. They rewrote it as like they pulled the negative out again and became 7x minus 3, and then they just canceled the negatives, but our answers are technically the same. And they also rewrote square root 4x as 2 times square root x instead of just square root of all over 4x. It's probably better, but I don't want to rewrite this now because I want to get through the problems. So let's look at this one. So this one isn't too bad either. We're going to do the same base idea, but see how this will work out. Yeah, let's see. Let me just see what questions we have left. Okay, I don't think we're going to get to page 12, but we'll try to get as far out as we can. 8 minutes left. Okay, so we're going to have okay, yeah, so we want to convert everything to base 2 here. My idea. So, and let's also just have like exponent side things on one side and normal other terms on one side. So let's just do 9x plus 5 divided by 2x equals 16 to the power of 3x plus 1 over 8 to the power of 4x plus 1. So now we can get base 2 on both sides, make it pretty neat. So we'll just do 2 to the 4 equals 16, and 2 cubed equals 8. So perfect. We figured out how to rewrite the bases. So it's just going to be 2 to the power of 4 times 3x plus 1. So that's just 2 to the power of 12x plus 4. And divided by 12x plus 3, because we're going to multiply 3 to both of those. So 2 to the power of 12x plus 3. And the key to this is we wanted it so we could just like subtract on the top and bottom with these. So just going to do a quick rewrite. So we're just going to quickly bring this up, and it's just going to be minus 12x plus 3. So you're just going to get minus 12x minus 3. So it's just going to be 2 to the 1 on the top on here. So you're just going to have 2 to the 1, and then let's just multiply the 2x back also. So we're just going to have 9x plus 5 equals 4x. So then you just get 5x equals minus 5. So, okay, so we're going to have like 5x equals minus 5. So you get x equals negative 1. Okay, so now, and this is just like a expand the log. So earlier we did a compressing the log. So this is like sort of reverse engineering it. But I want to look at the limits a little bit also because I think those are important. So I'm going to just skip this one for now. So find the following limits. So, okay, let's start with this one. And you're going to have x squared plus 3x minus 10 over x squared minus 4. So see what happens. Let's factor the top real quick. So if you factor the top, you're going to have a x plus 5. And you're going to have x minus 2 over x plus 2, x minus 2. It's the factor of x squared minus 4. And look at that. These cancel out. And this is basically like, well, I guess in this case, like if you had this function, as this is a function, these x minus 2's, like you would have a hole at x equals 2 because they cancel out. It wouldn't be a vertical asymptote, but it's fine. So let's plug in that 2 into the top and bottom. So you just get 7 over 4. So that's limit as x approaches 2 of that function equals this. I didn't want to rewrite the function, and I messed up my 7. So this is 7 over 4, so I'm just going to rewrite it here so it's not messy. So let's look at this one now. Okay, and this one's a little bit more interesting. It's a limit as you approach infinity. So, see this. So, first off, you have horizontal asymptotes. So, I'm pretty sure this is going to be going to infinity because like bigger on the top basically means like you're going to go to infinity, but we want to actually like show it like truly, right? So let's just divide by the biggest exponent on the denominator. So we're going to do 1 over x squared on the top and bottom over x squared. So when you multiply x cubed times 1 over x squared, you just get x. When you multiply 8x squared times 1 over x squared, you just get 8. And when you multiply 9 times 1 over x squared, you just get 9 over x squared. And when you multiply 1 over x squared on the denominator, x squared over x squared is just 1 minus 5 over x squared. And we just use a limit as x approaches infinity. And this should just be, so the point of this is if when we have x on the denominator as you approach infinity, that just makes that term 0. So here you just have like infinity plus 8 plus 0. You're probably not supposed to write like the actual, you're probably not like supposed to write infinity on there, but here, let me erase that. I don't think you're supposed to do that, but so we're just going to leave that as x for now. X plus 8 plus 0 over 1 minus, so 5 over infinity is going to be 0, so you just have, like, all you have left really is just, like, x, and, like, yeah, so all you have left really is x, and, like, a limit as x approaches infinity, that's just going to be infinity, so your answer is going to be infinity. And we could have already seen that with, like, the exponent rules, because it's bigger on the top, it would have gone to infinity, but doesn't hurt to actually prove it. So now for the final one, let's see. So for this one, you might think, okay, let's just plug in 4, but then you're gonna get 3 minus root 9, which is just 3, so that's 0. So that's no good. So we're gonna do a conjugate multiplication. And I think I skipped one earlier, so I guess this one will make up for it. Conjugate multiplication, so 3 plus square root of x plus 5 over 3 plus square root of x plus 5. So came out pretty nice, I would say. So the bottom is just going to be 9 minus, and make sure to put parentheses, x plus 5. It's not just minus x plus 5 or something. It's actually going to be multiplied to both terms over x squared minus 16 times 3 plus square root x plus 5. Square root x plus 5. So we're just going to have a quick. So the bottom is actually just going to become like 4 minus x. And we can rewrite that as minus x. So we're going to just get there. I'll just rewrite it without talking too much. So it's going to be 4 minus x on the bottom. And on the top, you're going to have this stuff. But let's just let's just factor that x squared minus 16 first. So we're just going to have x plus 4, x minus 4 times the conjugate, which was 3 plus square root x plus 5. And I'm just going to, so we want to cancel that out, but we can't really do that here because 4 minus x and x minus 4 are the same, but we can like sort of pull out a negative from this 4 minus x. So 4 minus x just equals negative x minus 4. So we'll just replace all of this with negative x minus 4. And then the x minus 4's cancel, so all we have left is just negative x plus 4 times this conjugate. And remember, I didn't forget about that negative 3 plus square root x plus 5. So then all you're going to have is, we're going to plug in 4, so it's going to be minus 8 times 6, which is just going to give you minus 48. And that's your answer. And I guess we'll call it a session here. The answer key in this recording should be available online. So I guess we'll call it here.
Thanks,
Test
Shriman, for
one.
leading the practice problem section of this tutorial. And thank you everyone for coming in. You can find this on like the YouTube channel, and if you're watching this currently, then in the description they have a link to find all the materials from today's session. Thanks, guys.
Yeah. See you guys later.